Hello all. In today's session we will talk about the next topic, designing a baseline model. So what a baseline model is, for example, this is my baseline model. So this baseline model can be considered to be as a benchmark or starting point. Based on this baseline model, your goal will be to design a model which is more sophisticated and more advanced than the baseline model. Like for example, the baseline model accuracy, what I have said is 70. That means your goal is to design another model taking this into consideration, and the model accuracy should be more than the baseline model. So this baseline model, what we will be designing, will be considered to be as a benchmark for the complex models what we will be using. So to design a baseline model, let us consider an AlexNet architecture here, one of the CNN architecture. It has 5 convolutional layers and 3 fully connected layers. Among 3, the third fully connected layer is nothing but the output layer. You can see here this is the first convolutional layer, second, third, fourth and fifth, and these 3 are the fully connected layers. The input image what I am using is 224 by 224 pixels. The filter what I am using for the first convolutional layer is 11 by 11, and 3 filters I am using. Stride size is 4 plus 1, which will be approximately equal to 55. So you can see here the first convolutional layer has image got reduced to 55 by 55, and for the next I will be using 5 by 5 kernel and so on. You can see that there is reduction in the dimensions of the image, and at the output of the fifth convolutional layer I have 13 by 13 by 256 that will be flattened and given as input to the first fully connected layer, next fully connected layer, and the output layer whose neurons are 1000. And here I will be using softmax activation function as it is multi-class classification. Rest all activation functions what will be used is ReLU. So this is what explained here. I have 5 convolutional layers and 3 fully connected layers. First convolutional layer filters are 96, you can see here. 96, 256, these are the number of filters used in each convolutional layer. And the size of the filter is 11 by 11, 5 by 5, 3 by 3. You can see here small boxes represents the filters which are used in the architecture. ReLU is the activation function used in all the hidden layers. And max pooling is performed at the first, second and the fifth convolutional layer. These 2 fully connected layers have 4096 neurons and the output layer have 1000 neurons, which makes use of softmax activation function. So this structure what we have designed will progressively reduce the spatial dimensions of the input image while increasing the depth, that is increasing the number of filters to capture various levels of features from edges in the early layers to more complex features like shapes and objects in the latter layers. Now we are ready with our baseline model. Now we need to make the data ready for training. For that purpose, we need to split the data into training and testing. The golden rule what you need to follow here is never use the testing data for training. That is, never use this test data for training. Perform training operation, calculate the error, update the weights, and find out the performance of the model depending upon the test data. Now we will talk about validation data also. After every epoch training, the training process, what do we do is we evaluate the model's accuracy and error to see how our model is performing. That is, how do we need to tune the parameters, that is weights and biases. So we cannot use this test data to find how our model is performing. So in that, the training data what we have used earlier, we will divide this training data split into training and testing. That's what we have done here. So this testing data is used for cross-validating the model what we have designed, whether it is performing properly or not. And the ratio what we use for training and testing is 80% for training and 20 testing, or 70-30 in most of the traditional machine learning algorithms. And if validation data set is introduced, we go for this ratio, that is 60 for training, 20 for validation and 20 for testing and so on. And this Ratio is applicable if the data set very small, but if we have large data sets, then it is fine to set your train and validation sets to much smaller values. Now that we have a baseline model designed, we are ready with our data. We have split the data into training and testing. Now we need to perform some operation on this data called as data pre-processing. That is, the raw data what is attained cannot be directly fed as input. We need to clean up that data called as data pre-processing. So we have different steps in pre-processing. Image grayscaling, you have image resizing, data normalization, and image augmentation. Image grayscaling is nothing but converting the colored images into grayscale images. Color images have 3 channels which will increase the complexity. So we convert it into grayscale image. Wherever colored images are not necessarily required for processing, in that we try to convert that colored images into grayscale images. Coming to the next application, next data pre-processing method called as image resizing. In neural networks, one of the limitation is if image is given as input to the MLP model, how many pixels I have in the image. For example, I have 256 pixel values, then I need to arrange 256 neurons in the first layer of my MLP model. Same is the case with CNN also. Depending upon the number of pixels, you need to arrange the neurons in the first layer of convolutional layer. This is the way how we call it in Keras. Conv 2D, add into the model with this many filters. This is the size, padding same, activation function, and input shape. 32 by 32 by 3. For example, if you are using 3 images and these 3 images are of different dimensions, then you need to resize this and make all the dimensions as 3, then only feed this data as input to the model. This is called as image resizing. Coming to the normalization, that is to standardize the data or to get the data into normal distribution, we try to normalize the data. So the characteristics which are required to make the learning faster is it should have small values, typically in the range of 0 to 1, and also it should be homogeneous, that is all the pixel values should be same. How do we normalize the data? We normalize the data by subtracting it from the mean and dividing it from the with the standard deviation. The same formula is applicable for training as well as testing data also. Same mean and same standard deviation is used for both training and testing to normalize the data. So here is the scatter plot of non-normalized data, subtracting that from the mean and dividing it by the standard deviation. So you can see that it got normalized to a standard scale. Here also another pictorial representation, actual data, I normalized it and got all the data points in one range only, so that it will be helpful for my model during training process. And the other application what I can see for normalization is, this is the contour of gradient descent algorithm. You can see here, to reach the minimum value, it takes the straight path if the data is normalized. Whereas if it is non-normalized data, then you have number of oscillations, that is it takes longer time to reach the minimum value. And the last method for data pre-processing is image augmentation. This image augmentation will increase the size and diversity of the image. And we have various transformation techniques like flipping, rotating, scaling, and shifting. Anyways, image augmentation will be discussed in the next topics. So this is the end of today's session. In the next session, we will talk about the evaluation of the model what we have designed. Thank you all.